Hello everyone. Today I'm coming from the University of Leeds and I'll be talking about my work using machine learning to deduce molecular weight distribution from, I should say, melt rheology. So, rich history of studying the forward modeling of molten polymers rheology from their material information, such as molecular weight distribution, including by Sam Edwards. And today we have good tube models, which, given an arbitrarily polydispersed molecular weight distribution, we can very accurately predict the storage and loss modulus representing the viscoelastic response of these materials. It's also an interesting challenge to try and reverse this prediction and get back to the molecular weight distribution from a simple rheology experiment, avoiding GPC experiments where maybe there's solubility issues, as was mentioned earlier, or in high volume cases where rheology experiment would typically be a bit quicker and easier. Now, the question is, can we reverse these models? And the simple answer for these advanced polydispersed models is not really. They don't have a nice closed mathematical form that is easy to invert. Some previous models do, but at this stage, we're finding it's pretty much not worth trying with these. So can we use neural networks and the advancements in that field and try and approximate the mapping back towards the molecular weight distribution that we're interested in finding? So with neural networks, the idea is to train on a large data set of artificially produced rheology data with this tube model. Can we train the neural network to get the molecular weight distribution? But how do we represent these data forms to the neural network? So for the molecular weight distribution, we have a sum of log normal or log Gaussian subdistributions here, which are just sort of imaginary components, but some of which can represent any broad polydispersed molecular weight distribution that we like. And we fix the mean molecular weights of each of these subdistributions so that all the neural network sees is the relative volume fraction of each. And then we do a similar thing with the rheology, which could come from lots of different sources. Different rheometers have different programming, and the rheologists themselves. So we fix relaxation times this time for each of these Maxwell relaxation modes and fit a relaxation spectra with the only variable that the neural network sees being the mode amplitude for each of these exponential relaxations. So the neural network is then trained on a large data set to try and recreate the molecular weight distribution with phi from these GI variables for the rheology. So the other problem is that we can do this for a certain polymer, or we can try and do it so that one neural network can try and predict the molecular weight distribution for any well-entangled polydispersed polymer. And to do that, we need to remove the material dependencies of the rheology measurement that we have. So to do that, we normalize the stress scale with the plateau modulus and the time scale with the entanglement time. And then for longer time scales for well-entangled polymers, the dynamics are completely dominated by the entanglements within the melt. So in theory, in this universal space of rheology, we should be able to train one neural network to predict a distribution of the number of entanglements with these two parameters here. And then with also knowledge of a third parameter, the mean molecular weight between entanglements, we can recover the molecular weight. And some results of that quickly. So these are two polystyrene polydispersed commercial polymers, and we train 9 neural networks. The training isn't deterministic, so that you train multiple and see how consistent your results are. And we get a good estimation of the weight average molecular weight and the polydispersity. And I'd invite you to see my poster for other results for other materials. Thank you for listening.